And the interface basically works like this. The GDB process tells the OS, start this new process, and stop it right after you start it. And then it can control it. You can, for instance, say, execute one instruction in that new process. Or start running a new process until maybe a system call happens. Or start running until it reaches a certain, reaches a certain PC, a certain program counter. But GDB can also control a process or program to be debugged that's not running on the same OS, but rather one that can be run somewhere else, as long as there is a stub program available that can control the execution of that program, and that stub can talk to GDB. So this is the setup that we're constantly using to debug operating systems in the 32.4 class. There we have an environment whereby we're debugging a kernel that runs in a virtual machine such as Box or QEMU. And Box and QEMU provide a GDB stub in that they can control the execution of the emulated virtual machine, and they can relate information about it back to GDB. So the GDB and the stub talk using a TCP connection, in this case using a certain protocol, and so control information goes from GDB to this environment, and runtime information, program state information flows in the other way. The most common use for GDB probably is to debug a segmentation fault. I should point out though that if you can run a program on the Valgrind, run it on the Valgrind first, because in this case Valgrind really supersedes what GDB does. I'll show you an example. Okay, so here's a program that produces a segmentation fault. Why does it produce a segmentation fault? We have a bunch of lists. A list has the next element, creating a bunch of lists here with different values, and then I'm starting to dereference them. First one, next one, next one, next one. Eventually, I'm trying to follow a pointer here somewhere that's a null pointer. I'm sure that this in fact segfaults, it does. I should point out, like I said, Valgrind, you should try that first. Valgrind also tells you, oh, there's an invalid read of size 4 at address 04. So maybe that's not as informative, I should say. So let's use GDB. In GDB, you run this program, and if you know it crashes, you just run it. It will run, and eventually it will crash. Now, at this point, when it crashes, okay, I should explain what happens here. When, quote unquote, what does crashing mean? So a program accesses memory, and that memory is not valid in its current address space. Okay, it refers to some address where there is no memory allocated, and as far as the contract is concerned between that process and the OS, this virtual address has not been provided to the user process by the OS. So the user process has not asked, I'd like to use this virtual address, okay, and therefore the MMU, the memory management unit, is programmed such that when that process accesses this memory, it will cause a page fault. Now that page fault traps into the operating system. In most systems, the operating system at this point will not terminate the process outright. Rather, it will send a notification to that process that says, hey, you just accessed memory to which you didn't have access to. And there are two cases. One is that the process either says, okay, I don't want to hear these notifications, just kill me, all right, and then you get the segfault message. But the process would also have the chance to intercept that message and do something else at this point. And so does the debugger. So if a program runs in the debugger and it experiences one such page fault, then the debugger is notified instead, and the process is stopped in its track right at this point where this fault occurs. And so now the debugger, meaning you, when you use GDB, you have the opportunity to examine the state. So at this point right here, the state of the machine is exactly as the fault occurred. You can use that to your benefit. So for one, you can say BT, backtrace, where does the segfault occur? Well, here, line 21. You can also use look at the instruction that caused it. For instance, You could say, what's the instruction that caused it? X/I. X means examine memory, I as an instruction, and look at EBP, which is stack pointer. So the defaulting instruction was this instruction here. Okay, this is a memory move instruction. Why did it cause a fault? Because the address that was being accessed must have been invalid, unmapped. The address here is computed by EAX plus 4, so you can look at what is the value of EAX. It is 0. Okay, so we know that this is the instruction that caused the fault, and why? Because address 4, which is 0 plus 4, was being accessed. Also, now, in most cases though, you don't want to go at the assembly level, you just want to look at the C level. So you run it, and GDB will print out the line that had the faulting instruction, or that contained the source code from which the faulting instruction was generated. So in this case, the faulting instruction was somewhere here, but you don't really know which one it is, right? There's 1, 2, 3, 4 memory accesses here. All right, but it's easy enough to find out how by simply typing this in. So this works, this works, this works. But this gets 0. So if you access this again, you fault. I should point out you can also use these dollar values here. So for instance, I can say $3 is 0, $2 is this, and so on. So once you get a fault, you simply use GDB and you use the print statement and you use C expressions to examine the state of the process. Any questions, thoughts about this? My experience is that I tell students, okay, so your program faults, use GDB to identify what's going on. If I have GDB, they bring it to the point where it falls, and then it's sort of lost. What do I do now?